Okay, I'm going to go ahead and do another demonstration on how to do transformations, but this time with a different parent function. As you can see on the graph here, we have a square root function. This parent graph is actually f of x equals the square root of x. And of course, we're still going to use our general form, af of b x minus c plus d. Now I know it's a little faint to see up here, but I actually have an equation, f of x, and then I have some numbers that's going to be moving as I move the equation around. But this is our parent function right here, just the square root of x. Now if you notice this time, we actually have a b. In the past, we haven't had a b, simply because of symmetry. But this time, we're actually going to have a b. This b is, for the square root, is either going to be a positive one or a negative one. If it's any other number, we want to pull it out and treat it like it's an a. I'm not going to give you any problems like that. Just to let you know there are times where this could be a number, and you would just pull it out of the square root, say like square root 2, square root 3, which is just a number itself. All right, so my a, it doesn't change. So as I move a, you can see the graph is actually getting pulled up as you see that the number here is getting larger. As when it's in between zero, when it's the absolute value, so like right here it's 0.7, you see this getting squished down. So we still have our vertical stretch, our A is our vertical stretch, and our vertical compression. That does not change. And of course then my C also is just moving it, it's our horizontal translations left and right. If you notice here in the right up here into the equation, as the graph moves this way, it is a plus, and as the graph moves this way, it's a minus, and that's because of the minus here for the C. It's actually opposite of what you're used to seeing. And then my D is still moving it up and down. Now, of course, if A is negative, it's a reflection over the y-axis. I'm sorry, a reflection over the x-axis. Woo! All right, now let's play with B. B here is either going to be 1, meaning that it's going to be opening towards the positive direction, or if I take it to -1, it reflects over the y-axis. So you can see when it was 1, it's facing this direction, and when I change it to -1, it just reflects over the y-axis. So it's still the same rule. It's affecting the x values. And as we do our transformations, what's really nice about this one is because it's either 1 or -1, we don't have to worry about multiplication or division. As you move on through different parent functions, that will come into play, not so much in Algebra 2, but definitely in pre-calculus, especially when we get to trigonometry. So let's do an example now. Okay, so we're going to do a pretty trivial example here. We still have my parent function, f of x equals square root of x. I've drawn in the general shape of the square root function, the graph itself. I didn't label any points on here because I actually want to show you how I pick my points. We could do it the traditional way of what we're doing is -2, -1, but those aren't even going to work in here. I still want to pick like 3 or 4 points so I get a pretty good feel for where the graph's actually going. What we're going to do here is we're going to graph g of x, and g of x is actually 3 times f of negative parentheses x plus 2 minus 1. So from there, we're going to pick apart A, B, C, and D. From there, we set up our vector mapping, do some basic math, sketch a graph. So the first thing I need to do is, on this parent function, what points I'm going to use, because that's going to be my starting point. Well, I'm going to pick 0, 0 right here. That's easy to do math with 0, 0. So I'm just going to do an x and y table instead of labeling up the graph here. So I'm going to start at 0, 0. Then I'm going to go to the first perfect square, which is 1. So I'm going to do 1, and I'll take 1, put it in here, square root of 1 is 1. Now I'm going to go to the next perfect square. Well, that's not 2, nor is it 3. So I want to pick 4. So at 4, I want to put 4 in for my x, I get 2. The square root of 4 is 2. And let's do one more. The next perfect square is going to be 9. And I put that in here. The square root of 9 is 3. So here are my points. They're not the normal points that we're used to using, like with the parabola or the absolute value function, but this one's got a little bit of different rules to it. So let's just dive in. So we're going to set up our vector mapping from our equation here, like we always have. The only difference is now I have a b. So let's just label it, figure everything out. A is actually going to be my 3 right here. My B, I want to choose -1 for my B because it's either negative, and I said but earlier in the video that my B for the square root is either going to be 1 or -1. My C, because this is a plus, I'm going to treat my C as like a -2 because it's minus a negative, which makes a positive. And of course my D is the -1. Now of course my A and my D affect my Y values, and my B and my C affect my X values. So let's make a table to actually find points that we can plot then and actually graph g of x. So let's put in our parent function points into our original part of our graph. So we're going to have 0, 0, 1, 1, 4, 2, 9, 3. We're going to augment our table. And from here, we're going to go ahead and pick what exactly is going on with our vector mapping. Well, now that I have a b, this b is going to be -1, and because I'm multiplying here, I'm going to multiply my x by a -1. And then, of course, we are going to subtract my 2, because my c is -2, because it's +2 here. It's counterintuitive, it's opposite. My y's, they don't change. So I've got 3y, because I have 3 times f of x, basically. So that's 3 times a y, -1. We just plug in the points. Well, 0 times a negative is 0, and then this becomes -2. Put this in, I got -3, -6, -9, -11. So there are my new x values, -2, -3, -6, and -11. Hopefully I did my math right. Put my 0 in here, I got a -1. This gives me 3 minus 1, which gives me 2. 6 minus 1 gives me 5, and 9 minus 1 gives me 8. So my new points are -2, -1, -3, 2, -6, 5, -11, 8. So all we have to do is now graph these, sketch, make sure our sketch looks like our original parent function over here, and we are all done. So let's just put in a pretty basic XY plane. I don't really care about it being real precise. Unless I give you graph paper and they're pretty points like this, then I would want you to label it and then label your scales and everything else. All right, so here we go. We've got -2, which is on this side of the origin, -1, so it's down here somewhere. We have a -3 and a 2, so that's going to be above. Then we have a -6 and a 5, which is higher up. And then a -11 and 8, which is higher up. So my graph would look something like this when we do the actual graphing itself, which actually would make sense. If you just think about it, we're actually stretching it by a factor of 3. So it's gotten a little higher. We are reflecting it over the y-axis. We are moving it left 2 units. We're going this way 2 units, and then we're going down 1 unit. So the picture itself actually makes sense if you actually describe each individual transformation. Of course, you know, we are going to do also cube roots. What's nice about cube roots is we no longer have that b again. It's back to just a, c, and d. Only certain functions in Algebra 2 are going to have this b in there, and when there is, it's going to be either a +1 or a -1. You won't deal with another number until pre-calculus. Hi, I'm Mr. Buzzard, and I'm making these videos as supplemental instruction for my students. If you found these videos actually informative or they answer the question you're looking for, make sure you hit the like button, and then don't forget to subscribe and then click the bell to receive notifications for future instructional math videos.